Vision Large Language Models, or VLLMs, have made remarkable strides in artificial intelligence, particularly in handling tasks that combine images and text. These models can generate detailed descriptions of pictures, answer questions about visual scenes, and even create content that bridges visual and linguistic data. However, their performance in specialized and high-stakes areas, like autonomous driving, has not been thoroughly tested until now. The key question this research addresses is whether these VLLMs are truly ready for real-world deployment in safety-critical scenarios, such as driving on busy roads or navigating unexpected hazards. Autonomous driving systems rely on accurate perception and reasoning to interpret complex environments, making split-second decisions that could save lives. While VLLMs excel in general tasks, they haven't been evaluated extensively in these demanding contexts. To fill this gap, researchers from Virginia Tech introduced a new benchmark called DVBench. This benchmark is specifically designed to assess how well VLLMs can understand and reason about safety-critical driving videos. DVBench is built around a hierarchical taxonomy of driving abilities, which draws from established frameworks used in evaluating highly automated driving systems. This taxonomy includes categories like atmospheric conditions, road surface conditions, traffic hazards, vehicle maneuvers, and event characteristics, covering 25 distinct abilities in total. For instance, the benchmark tests a model's ability to identify visibility constraints, such as fog or rain, evaluate road geometry like curves or intersections, or analyze traffic control devices like stop signs and traffic lights. By organizing questions this way, DVBench ensures a comprehensive evaluation that goes beyond simple object detection to include deeper reasoning about cause and effect, fault analysis, and potential risks. DVBench consists of 10,000 multiple-choice questions, each paired with human-annotated ground truth answers. These questions are derived from real-world driving videos, focusing on rare and safety-critical events that are often underrepresented in existing datasets. This approach addresses a major challenge in the field: the rarity of dangerous scenarios in typical driving data. For example, datasets like NewScenes, BDD, and Waymo Open are mostly filled with routine driving situations, which can lead to misleadingly high accuracy for models that simply guess common outcomes, like going straight ahead. In their experiments, the researchers tested 14 state-of-the-art VLLMs, with parameter sizes ranging from 0.5 billion to 72 billion. Models included popular ones like LLAVA1 Vision, Qwen2VL, and others. The results were eye-opening. Across the 25 abilities in DVBench, no model achieved an accuracy higher than 40%. This significant performance gap highlights critical limitations in how these VLLMs handle complex, dynamic driving scenes. For example, they struggled with understanding spatial relationships between objects, predicting event severity, or reasoning about environmental hazards. To visualize this, the researchers presented a figure showing the performance of 9 representative models. It illustrated that even the largest models, with up to 72 billion parameters, fell short in many areas, such as interpreting traffic conditions or construction zones. This underscores that sheer model size doesn't guarantee effectiveness in safety-critical applications. Instead, the models need better adaptation to domain-specific challenges. Encouragingly, the study also explored ways to improve these models. By fine-tuning selected VLLMs using domain-specific data from DVBench, the researchers achieved notable accuracy gains. Specifically, accuracy improved by 5.24 to 10.94 percentage points, with some models showing relative improvements of up to 43.59%. This demonstrates that targeted training on safety-critical driving data can bridge the gap between general-purpose VLLMs and the rigorous demands of autonomous systems. The implications of these findings are profound for the development of reliable autonomous driving technology. They emphasize the need for benchmarks like DVBench to guide future research, ensuring that VLLMs can handle not just everyday driving but also unpredictable and hazardous situations. By releasing the benchmark toolbox and the fine-tuned models on GitHub, the researchers have provided a valuable resource for the community to build upon. In summary, this work reveals that while VLLMs have impressive general capabilities, they are not yet road-ready for safety-critical driving tasks. Continued efforts in creating specialized benchmarks and adapting models will be essential to achieve the safety and robustness required for real-world deployment. This research paves the way for more effective vision language models in mission-critical applications, ultimately contributing to safer autonomous systems.